Okay, so what I want to do now is discuss convergence in measure. This is going to be section 5.2 in the textbook. So yeah, we've actually already seen this before in the exam too. So let's say we have a sequence of functions and a function on E, all measurable. We say Fn converges to F in measure on E if for any positive nu. I think this is nu. If not, we're going to use this. I'm going to call this nu for the rest of the video. So for any nu positive, this limit is going to be equal to 0. So what are we really saying? We're saying for any nu, tiny, it could be really, really, really small, doesn't matter. The set x and E where Fn of x minus f of x in absolute values bigger or equal to nu can be made arbitrarily small by setting n large enough. Or in other words, for any nu positive, for large n, Fn of x minus f of x absolute value is less than nu for most, or rather on most of E, in the sense that the set where that is false can be made arbitrarily small in measure by making n large enough. Okay. So in the exam 2, you proved that if Fn converges to F pointwise on E, and E has finite measure, then Fn converges to F in measure. Okay? And yeah, the proof was very easy. It just it was essentially part of the proof of Egorof's theorem, except for one tiny little piece, and you put that piece together on the exam. So you might ask, well, what happens when m, the measure of E, is infinity? Is this true? Does pointwise convergence imply convergence in measure? And the answer is no. And you can come up with easy examples similar to this. So particularly, let's say Fn of x is this characteristic function from n to n plus 1. Let's define f of x to be 0 on E. Clearly, Fn converges to F pointwise on E. In particular, pick any x. If n is bigger than x, then certainly x is not between n and n plus 1. So Fn of x is 0. So for n larger than x, Fn of x is 0. So the limit as n goes to infinity of Fn of x is 0. Okay, now let's look at the measure of this set here. Anything strictly between 0 and something less than or equal to 1 works. 1/2 is simplest. All right, so of course this here is 0. This here is characteristic function of n plus 1. All right. So we're saying, when is the characteristic function bigger or equal to 1/2? Well, it's exactly when we're on the set associated to this characteristic function. And that's exactly n to n plus 1, particularly because n to n plus 1 is always a subset of 0 to infinity, as long as n is positive. Right. So this set here is trivially n to n plus 1. That has measure 1. So this limit here is, well, miserably fails to be 0. It's 1. Okay. So this is an intriguing example because what's going on here? Well, for Fn of x, obviously, it's 0. It's the horizontal line 0. And then we hit n. And then it becomes this rectangle. And then we go back to being 0. And this, the rectangle, this hump, kind of shoots off to infinity as n goes to infinity. So you might wonder, you might wonder with maybe skepticism, because this hump shoots off to infinity, could you cook up a similar example to work where E has finite measure? And the answer is of course not, because, well, in the exam too, you proved that pointwise convergence implies convergence in measure, as long as we have a set of finite measure. And you might be wondering, well, what about the converse? Does convergence in measure imply pointwise convergence? And the answer is no, right? Even if we have a set of finite measure, the answer is still no. So let's take our E to be 0 to 1. Let's say I1 is, excuse me. Let's say I1 is 0 to 1. I2 0 to 1/2, 1/2 to 2 over 2, and repeat this pattern. I4 0 to 1/3, 1/3, 2/3, 2/3 to 3/3, etc., etc. So I11 would be 3/4. Sorry, I11 would be 0 to 1/5, etc., etc. So to get a grasp on IK for basically arbitrary K, what we're going to do is we're going to identify when we get 0 to 1 over 0 to 1 over an integer for each integer. Particular, it occurs well right here. So it's I1, I2, I4, I7. Then it would be I11. Right. So I claim, and it's not hard to prove this, that if nk is this integer for k, a natural number, then ink is 0 to 1 over k. So let's just check it for a few different k. K equals 1 is trivial. It's just 1, 0 plus 1. I1 is 0 to 1. K equals 2. It's going to be 1 times 2 over 2 plus 1 is 2. I2 is 0 to 1/2. K equals 3. 3 times 2 over 2 plus 1. I4. I4 is 0 to 1/3, etc., etc. You can plug in K equals 4, K equals 5. Like K equals 5 would be 4 times 5 over 2 plus 1 is 11. I11, 0 to 1 over 5, based on this pattern here. Okay, and I should make clear we're defining nk to be this integer here, and when we do that, we're claiming ink is going to be this interval. So we checked it for k equals 1. Let's assume it's true for k, so ink is 0 to 1 over k. We're going to prove it for k plus 1. Now notice that ink plus 1 is just 1 over k to 2 over k. Ink plus 2 would be 2 over k to 3 over k, etc., etc., until we get to k minus 1 over k to k over k. And then the next one, we're going to go back to 0 in the numerator and k plus 1 in the denominator. That's just how we're defining this pattern. Okay? So we know that if this is true, so if what I'm about to circle is true, which is our inductive hypothesis, if this is true, then ink plus k is 0 to 1 over k plus 1. Okay, we just showed that, right? We just pretty much trivially showed that. So it's enough to show that nk plus 1 is nk plus k. We're defining nk in this way. Because then ink plus 1 is ink plus k is 0 to 1 over k plus 1, and that's exactly what we want to show. And this is very easy. Nk plus k, this is what nk is. Add k to it. K squared over 2 minus k over 2 plus k. So write k as 2k over 2. So it's going to be plus k, should be k over 2. And this is k plus 1 over 2 plus 1. And that's nk plus 1. Very trivially because, well, not much to that. Plug in k plus 1 here, you get k. Plug in k plus 1 here, you get k plus 1. So it's k plus 1 over 2 plus 1. All right, so that proves it. So now we can prove convergence and measure of these characteristic functions very easily. Sorry, convergence and measure to the 0 function on 0 to 1. Okay. How do we do that? Well, let's look at this set here. Let's say nu is positive. Let's say this is positive. Okay, so again, this is 0. And this here is just a characteristic function, in of x. So if nu is bigger than 1, then this set here is empty. Characteristic function is never bigger than 1. So in that case, it's certainly less than or equal to the measure of in, which is not negative. If nu is strictly between 0, if nu is positive but less than or equal to 1, then the set where the characteristic function is bigger or equal to nu is just in, particularly because in is, each one of these is a subset of 0 to 1. So then this the measure of this set is the measure of in. Okay? Either way, it's less than or equal to the measure of in. So we need to show that this limit is 0, and that is very easy. Pick epsilon positive, pick k bigger than 1 over epsilon, pick n equal to 1/2 k minus 1k plus 1. Then in, because n is, big N is exactly this little nk we just defined a moment ago, big N is 0 to 1 over k. Okay? And remember the pattern for, let's say, big N plus 1. It's just going to be 1 over k to 2 over k. Big N plus 2, 2 over k to 3 over k, until we finally get to in big N plus k minus 1. It's going to be k minus 1 over k, k over k. And then big N plus k is going to be, start over again, 0 to 1 over k plus 1. The point is, if little n is bigger than big N, then we either have the same denominator or a larger denominator. Okay? And of course, for whatever denominator we have for our intervals, that denominator specifies the width of each of these intervals is 1 over that denominator. That's just fairly obvious. I mean, that's the way these intervals are defined. Okay, so first of all, the measure of in is 1 over k is less than epsilon. And if little n is bigger than big N, then the measure of in is the width of each of these intervals, which is 1 over some denominator that is larger or equal to big N. And therefore, its measure is less than or equal to the measure of 1 over big N is less than epsilon. So we easily have convergence in measure. Okay. Now I claim that for any x between 0 and 1, I can find an increasing sequence of integers where fnk of x, nk prime, because nk we already used for, when we have 0 to 1 over k for our intervals. But anyway, so I can always find, for any fixed x, I can find these integers where fnk prime of x is 1. These are going to depend on x, but that's okay. By the way, if you're wondering, this is my digital pen, and this is my digital pad, XP pen. I like it. It was 30 bucks. No complaints so far. I don't have a good reason why you shouldn't get a actual iPad or something like that. I'm just cheap, so I got something crappier and 30 bucks. But anyway, back to the scheduled programming. So, right, if I can do this, then obviously this limit is not 0. So Fn converges to 0 in measure, but miserably fails to converge to 0 point-wise for any x in 0 to 1, not just some x. Any x, this does not converge to 0 point-wise. Okay, so let nk be as before. So in other words, nk is, sorry, where did it go? Nk is just this integer right here. Okay? So let ink is 0 to 1 over k. So we're not going to let nk, well, let's see what nk prime is going to be. Okay. So do something you've done absolutely in basic analysis to prove that rationals are dense in the real line, or 0 to 1, or any subset of the real line. Particularly for this fixed k, where k is an integer, let's say little m is possibly 0, but it's an integer, non-negative integer less than k, and pick little m where x is between mk and m plus 1k. Okay. Set little nk prime to be nk plus m, so that if fnk prime of x, so because of this, fnk prime of x is just this characteristic function, but this characteristic function, or sorry, this interval is exactly, well, what are we doing? Nk is the interval 0 to 1 over k, so we add m to it, particularly we add m, which is less than k, to nk. Well, instead of going from 0 to 1 over k, it's m over k to m plus 1 over k. That's exactly how our intervals are defined. And x is in this interval. That's how we picked m, actually. So this is going to be equal to 1 for every single x and every single nk prime. Of course, nk prime depends on x because m depends on x, but that's okay. All right. So let's just finally note that these are strictly increasing. Well, that's fairly trivial. Nk prime is nk plus m. M is strictly less than k. So this is nk plus k, which remember is nk plus 1. Okay. And again, nk plus 1 prime is nk plus 1 plus some non-negative integer, depending on x. So this is bigger or equal to nk plus 1 prime. So in particular, whoops, let me do that. So this here is less than this here, strictly less than. Okay, so you'll notice something interesting, and that is we can pick a subsequence of these characteristic functions. So, right, we can pick a subsequence of these characteristic functions here that converges almost everywhere point-wise to 0. And in fact, we have convergence on all of 0 to 1, except at 0 in this example. So let's just say, what's that subsequence? Well, just, I'll go down here. Just pick nk to be the characteristic function of ink. What's ink? 0 to 1 over k. For every x, if k is big, so for every x strictly positive, pick k larger than x, so that x is larger than 1 over k. Sorry, pick k strictly bigger than 1 over x. So then 1 over k is strictly smaller than x. So x is not in these intervals for large enough k. So that f and k of x for each x for large enough k is 0, okay? As long as x is not 0. Okay, so I claim you can always do this. You can always pick a subsequence that converges to your function. Well, not always exactly on all of your e, and we just showed that. We do not have pointwise convergence at x equals 0. Fn of x is 1 for every single n whatsoever. Okay. Okay, so yeah, if we have convergence in measure, then there exists a subsequence where fnk converges to f pointwise almost everywhere on E. And this is a beautiful proof. It uses Borel-Cantelli in a very beautiful way. So what do we know? We know this limit is 0. I'm setting nu. This is my nu here. It's small, but it's positive. Okay. So let's pick an nk. So I can so for large enough n, so let's say epsilon is positive. For large enough n, this is less than epsilon. Let's say epsilon is 1 over 2 to the k. So pick big nk where this measure is less than 1 over 2 to the k if n is larger than nk. Yeah, just definition of this limit equals 0, nothing more. Okay, so we're almost done picking our subsequence, actually. The only issue is that we don't know if these big NKs are necessarily strictly increasing. Remember, for a subsequence, you have to have n1 strictly less than n2, strictly less than n3, et cetera, et cetera. That's easy to handle. So pick n1 to be big N1, little nk plus 1 to be the maximum of these plus 1. So what does that mean? By this definition here, this is certainly bigger or equal to nk plus 1, and obviously this is, well, it equals big N1. So little nk is always bigger or equal to big nk. And this is strictly increasing now because nk plus 1 is a maximum of these two. So in particular, sorry, it's a maximum of these two plus 1. So it's certainly, this maximum is bigger or equal to little nk. It could be little nk, but certainly bigger or equal to little nk. Well, because we add 1, it's strictly bigger than little nk. Right, so it's strictly increasing. Okay, so let's say ek is this set here. Little nk is bigger or equal to big nk. So this set has measure less than 1 over 2 to the k. So if I sum these measures up, I get 2. I don't really care. All I care about is it's something positive. So I could have set this to be 1 over k squared, and the sum would be pi squared over 6. We don't care. We just want it to be summable. Because if it's summable, Borel-Cantelli says almost every x in E belongs to finitely many of the sets Ek. Okay. So I claim that if x belongs to finitely many of these sets, then we have pointwise convergence. Why? Pick such an x. Let's say epsilon is positive, and let's say k is bigger than 1 over epsilon. For possibly larger k, let's say, well, x belongs to only finitely many of these EKs, so for large enough k, x is not in any of these sets. Well, if x is not in any of these sets for large enough k, then this quantity here is less than or equal to 1 over k. which is less than epsilon. So for each x, particular for each x satisfying, well, this condition here that I'm going to underline, and we know almost every x satisfies this. The set where this is false has measure 0. So for every x satisfying this, for large enough k, absolute value of fn k of x minus f of x is less than epsilon. Right? Where k possibly depends on epsilon, right here. Because we're assuming k, we're picking our a priori k bigger than 1 over epsilon. So that converges, that proves the pointwise convergence of this subsequence. Okay. So I want to very briefly mention L1 convergence, which is convergence in this sense. Okay. Excuse me. Okay, so if this is true, then it's a very easy homework exercise using Chebyshev's theorem, or Chebyshev's inequality rather, that we have convergence in measure. It's really, really easy, which illustrates the utility of Chebyshev's theorem. Okay, and the converse, I should mention, even when E has finite measure, is false. Convergence in measure does not imply you have this convergence here. So there actually is, interestingly enough, the book in section 5.2 has a characterization of when, it gives a precise relationship between convergence in measure and this L1 convergence. And it uses concepts that are fairly advanced. If you want to look, it uses uniform integrability and tightness. Which is, yeah, these are technical things you would study in detail if you take a serious probability course, you know, a graduate level one. But anyway, so the converse is false, and I'll leave for you for homework to check that this example shows that the converse is false, that convergence in measure does not imply. I should mention here. E is 0 to 1. So yeah, you can check that this fairly trivially converges to 0 in measure. I mean, I don't want to say anything more because it's really hard to even give a hint as to how to prove that without proving it. It's so easy. And you can check that Fn does not converge to 0 in this sense here. Again, that's even easier. And yeah, that finishes this video. So what I want to do in the last video is, instead of really doing anything terribly new and difficult, I want to mention how, very, very briefly, how these things can be, everything we've done can be used to study probability theory. And in particular, I want to probably prove the 2 Borel-Cantelli lemmas for probability theory. I'll prove the second one, which is a quite interesting proof, and it utilizes independence, and all. You know, we've all seen independence before in probability theory, but I'll mention that. And I'll leave one of the Borel-Cantellis for homework. It's basically the same proof as in the book. But anyway, so yeah, so just remember, one more week and we are done. So hold tight. Who knows what the fall is gonna bring us, but at least for now, we got one more week. All right, so long, take care, and yeah, I will be in touch with everyone soon. Bye-bye.